If I asked you who wrote the first computer program in history, you would expect a clean answer. One name, one date, one neat little snippet of code. But the truth is, the first program isn't a file that you can run. The question gets debated because defining how the first program came about is not easy. It's debated because we are arguing definitions. What program means, what counts as evidence that you wrote the first program, and whether first means the first idea of a program, or the first program published on paper, or the first program actually executed. So, who wrote the first program? It's either a Victorian countess called Ada Lovelace. It's a very seductive name. Or it's this guy building a steam-powered computer in his living room. He was called Charles Babbage. Maybe not so seductive of a name. Babbage created the design for a machine called the analytical engine. And when I say created, I mean designed it. It was essentially the blueprint for a general-purpose computer. But it wasn't a finished machine sitting on a desk somewhere. Then Ada Lovelace came along and wrote what looks to be a real program, which was an algorithm intended to run on this machine. It was never executed in a lifetime, but on paper, the logic was there. So, if the machine was Babbage's, did he invent programming by imagining a programmable computer? Or does the title belong to Ada because she wrote the instructions even though they never ran? If you Google who wrote the first program in history, you'll see phrases like Ada Lovelace has been considered the first programmer. So what are we actually crediting Ada for? And does she really deserve the title of the first programmer? Before we figure out how it all started, thank you Airia for sponsoring this video. So we have Ada Lovelace, who laid out the first algorithm by hand for a machine that didn't even exist. Fast forward 180 years later, even with all the tech we've built, companies today are still struggling with that same core idea. How do you get machines to follow complex instructions, read data, and actually deliver value? Airia is an enterprise-grade AI orchestration platform that helps organizations build, manage, and scale intelligent agents. Let's just say you are a large financial company, and your legal and compliance team needs an AI assistant to review contracts, flag risky clauses, and summarize changes, but only using your internal documents and policies. With Airia, you can build that agent quickly, plug it into your secure data, and deploy it across your organization with all the guardrails you need, things like privacy, auditing, and version control. It is also model agnostic, meaning that you can use OpenAI, Google Gemini, any open source models, or your own, and you don't need to write custom pipelines for this. Airia brings structure to AI chaos. No more disconnected tools, rogue bots, or shadow AI projects. Just one platform for building agents that actually work and scale. Airia is helping enterprises today actually put AI to work securely, efficiently, and responsibly. Check out airia.com or use the link in the description to see how it all works. Any hunt for the first program must start with Charles Babbage. He was the English polymath who designed something called the analytical engine. The analytical engine is now what we recognize as the world's first general-purpose computer. It was conceived in the 1930s, 1940s, but Babbage's analytical engine never was actually built because of funding limits and even engineering limits. But on paper, it was decades ahead of its time. He didn't build the machine to be a simple calculator. The machine was designed to execute the whole of development and operations of analysis. This means that it could run any calculation that can be formulated, no matter how complex that calculation is. If you look at it on modern terms, the analytical engine would have been a Turing-complete computer, and it had a structure very similar to a modern CPU and memory system. To understand how epic this design was, let's break it down in parts. To see why the analytical engine was ahead of its time, it helps to picture it less of a calculator and more of an early mechanical version of a computer. So the analytical engine had a central processing unit that Babbage called the mill. The mill was the part that actually did the math, very similar to a CPU. It was a big mechanical workshop where numbers get carried in, worked on, and then sent back out again. There was gears, shafts, levers, and these would represent the digits and the control steps in the operation. Then there was a store, which was the memory of the engine. It was basically RAM, memory before electricity. So Babbage here imagined rows of numbered wheels that could hold a number, and that machine could fetch the number from the store, send it to the mill, then put the result back to the store again. And remember, the fetch, compute, store loop is the heartbeat of modern computing. You then get punch cards. Now, Babbage didn't want people to rewire the machine every time they wanted a new task. He wanted it to be programmable, and punch cards were his solution. Babbage got the idea from the Jacquard loom. This was a weaving machine that used punch cards to automate patterns. So in the loom, you would feed a punch card, and each card described one row of pattern. Holes in the card means lift this thread. No holes means don't lift the thread. And eventually the loom would actually weave a specific pattern. If you change the card, you change the pattern. So same machine, different instructions. Basically the concept of programming and software. So Babbage took this loom idea and made it more computer-like by separating the cards into different roles. He had operational cards. These were cards to determine what action to perform, multiply, add, compare, etc. There was also variable or constant cards. These included the values to work with, the inputs, and then there were transfer cards as well. And these were cards on how to move numbers from the store to the mill. Now, in modern programming languages, that is the beginnings of separating instructions from data and also introducing the idea of moving data around intentionally, a huge part of programming. It was basically the blueprint of a computer. Physically, had the analytical engine been built, it would have been enormous. Babbage's plans call for a machine that was over 4 meters tall and 6 meters long. It was likely also to be powered by a steam engine. And it was a good thing that the machine was never built because it would have sounded like a factory when running. But on paper, Babbage had actually sketched out 28 different ideas or plans for the machine. Now, the most famous plan, Plan 25, this was in 1840, was a version he presented in Italy, and it's a version that became famous. This is a version that Italian engineer Luigi Menabrea wrote about, which brings us to the hero of our story. So enter Augusta Ada King, Countess of Lovelace, better known today as Ada Lovelace. Ada was a daughter to a poet called Lord Byron, but thanks to her mother's determination that she does not become a poetically free spirit like her father, Ada was actually given quite an unusually rigorous education in mathematics. And she was growing up in a society that didn't really encourage women to pursue anything in STEM or science, and Ada really just developed a passion for math and science. As a teenager, Ada became friends with Mary Somerville, who was a noted mathematician and scientist, and through her she was introduced to Charles Babbage. Now in 1833, Ada was 17, and she saw a prototype of Babbage's earlier engine called the difference engine, and she was just absolutely enchanted. Babbage himself took note of Ada's keen intellect. He would later dub her the enchantress of number, and this meeting actually sparked a long collaboration and friendship. So fast forward a decade or so. It's 1840s, and Babbage was campaigning across Europe to drum up some interest and funding for his analytical engine. At this stage, the British institutions have grown wary of Babbage and his expensive projects. So in 1840, he gave a series of lectures in Italy, and it was attended by a young engineer called Luigi Menabrea. Menabrea wrote up a detailed description of the analytical engine in French, essentially the first published account of Babbage's engine. And Ada, who had been looking for a way to make her mark in science, was asked by another friend to translate Menabrea's French article into English. Interestingly, Babbage himself actually encouraged Ada to take on this task and even add some notes of her own to clarify and expand the ideas. Her results were published in 1843 in English in Taylor's Scientific Memoirs, and it was monumental. Ada's translation and her extensive notes came out anonymously. She signed it AAL. People who read it realized something special. The original Menabrea article in French was about 20 pages, while Ada's supplemental notes were about 40 or more pages. And in these notes, Ada had explained the functioning of the analytical engine in more clearer terms than Babbage ever had. She even mused about its potential uses. She wrote about the machine in a more visionary way than Babbage, foreseeing that this engine might act upon other things besides number. Potentially, it could compose music or even graphics. And most importantly for our quest, Ada's note G in that paper included something unprecedented, a step-by-step method for the engine to calculate a sequence of numbers known as the Bernoulli numbers. And this is a piece that is often cited as the first program. So Ada wrote some notes to expand on Charles Babbage's analytical engine. In one of the notes, note G, she created a step-by-step method for the engine to calculate the Bernoulli numbers. And in Ada's time, Bernoulli numbers were already known amongst mathematicians. It was used heavily in 18th to 19th century calculus, etc. It was a very popular calculation. So for example, imagine you're in the 1800s. You want to calculate the distance a cannonball will fly. You're dealing with curves, not straight lines. You're dealing with the arc of a projectile. So you need to know the area under the curve in order to see how far something travels. Now, in the 1800s, there were no calculators, so you would have to do this all by hand. It would take ages. And calculating the area under the curve requires estimating the sum of changing values, like slicing the curve into tiny pieces, figuring out the height of each one, and then summing them all up. So there was a formula for this called the Euler-Maclaurin formula. And this estimated the area under the curve using just fewer calculations and some correction terms. The correction terms here are Bernoulli numbers. So the Bernoulli numbers are fractions that actually appear in many areas of numbers. They often come up with formulas dealing with sums, fractions, and patterns. In higher level maths, it's not an easy calculation. And the key part here is that you don't need to know them all up front. If you know the first few Bernoulli numbers, you can calculate the next ones using a set formula. This is known as a recursive pattern, very popular in programming, where the new number depends on previous numbers. And this is why it's a perfect problem for a machine to solve. So Ada wanted the analytical engine to calculate the Bernoulli numbers, one after another. She wasn't interested in just one answer. She wanted to show that the machine could loop through steps, use memory to recall past values, and make decisions. So if I reach the end, I need to stop. And this was programmatic thinking 100 years before real computers. So Ada's note G actually walks through how the analytical engine could, in theory, compute Bernoulli numbers. Again, definitely not the most simplest of calculations. She even stated the object is not simplicity or faculty of computation, but the illustration of the powers of the engine, meaning it's a hard formula. So Ada used this sort of mathematical definition. And if you translate it into modern programming, it looks something like this. So if you break it down, the program starts with two known values, B0 and B1. It then loops through to calculate the next values, B2, B3, B4, and so on. Inside the loop, it adds all the needed earlier values using a specific formula. Then it divides it and then stores the result for the next Bernoulli number. And Ada actually showed how this could potentially work by manually doing the calculations on a table. And this logic is exactly what Ada traced out manually, row by row, using variables like V1, V2, V3 to represent the stored values in the engine's memory. You can see it here. So this means that Ada's algorithm wasn't just some sort of math trick. It used the core ideas of programming. There was loops, memory, and conditionals. And she did this all by hand. So in Ada's lifetime and decades after, people have often wondered how much of the program that she wrote was actually Ada's own work. Charles Babbage was the inventor of the machine. So perhaps he already sketched out this program and Ada was merely reporting on it. Or maybe Babbage heavily guided her through it. And this question of credit has led to some persistent debate amongst historians. Here are the facts as we know them. Babbage and Lovelace did correspond intensely while she was preparing the notes. They were really in constant communication. Ada was asking detailed questions about how the engine could do X or Y, and Babbage actually providing answers and suggestions. Babbage later wrote, "We discussed together the various illustrations that might be introduced. I suggested several, but the selection was entirely her own." He added, "The algebraic working out of different problems in the notes was entirely her own. except indeed that relating to the numbers of Bernoulli, which I had offered to do to save Lady Lovelace the trouble. This she sent me back for an amendment, having detected a grave mistake I had made in the process. In plainer terms, Babbage claimed that he offered to actually write the Bernoulli computations for Ada, but she just went ahead and did it. And when he tried to help, she even caught an error in his work. And this quote from Babbage is a very strong acknowledgement that Ada was definitely in the driver's seat of Note G, even if Babbage himself had provided the initial formula or guidance. So why do some people challenge Ada's status as the first programmer? One reason is that Babbage himself has designed programs for his engines previously, but none of them were published in a way that Ada's were. There was a historian called Alan Bromley, and he noted that Babbage had prepared several dozen programs for the analytical engine between 1837 and 1840. And in his notebooks, these included routines for tasks like a polynomial evaluation, solving equations, and even a version of Bernoulli number calculations. So technically, one could say Babbage himself wrote the first programs on paper, since he developed the algorithms his machines could use before Ada got involved. But Babbage's programs were not widely known at the time. They remained in his notebooks. And they were written in very rough form, since he never worked out a full, complete sequence like Ada's Bernoulli table. Ada's work was the first published and fully articulated program intended for public understanding. And that made the difference. So, who wrote the first program? If you define program as strictly a sequence of operations coded for a machine, then Ada Lovelace's Note G algorithm from 1843 is the one. It's the first to be published, first to be fully articulated, and first to be explained to the world. This is why she's widely celebrated as the first computer programmer. But it is clear that she didn't work in a vacuum. Babbage provided the concept of the machine and had thought about the automation of calculations. And the best way to see this is a collaboration. Babbage built the piano, and Ada wrote the real first piece of music. Both roles indispensable to the history of programming. But it's definitely not incorrect to say that Ada Lovelace was the first computer programmer. Thanks so much for watching. If you like my content, please like, comment, and subscribe. I'll see you in the next one. Bye.